Okay, before I go on with some examples with phase margin, I just wanted to show you this little graphics and make you aware of this relationship. Here we have we work our math backwards and do some interesting things with our math. We can come up with an equation that relates our phase margin and our zetas. Okay, remember zeta. Zeta is the damping ratio. The smaller the damping ratio, the more oscillation we get in our system. The higher the damping ratio, the less oscillation we get. And then here shows the graph between phase margin and damping ratio. So as our damping ratio goes up here, then our phase margin also goes up. Okay, so what this means in terms of our Bode plot is if we don't want a lot of oscillation, we need to have a high phase margin. The lower the phase margin is, the more oscillation we're going to have in our system. Okay, so there's a direct relationship there that we need to be mindful of as we start doing our design, because we could do some designs that seemingly improve the performance, but what ends up happening is that you introduce a lot of oscillation in there. So kind of be mindful of this. That's the reason we have that minus 20 dB per decade through the crossover frequency, to try to maintain a high phase margin so that we minimize the oscillation of our system.